Okay, so now we started 1D problem and single degree of freedom, and then 2D problem, again single degree of freedom, and then we talk about 1D problem with multiple degree of freedom, like a 2 degree of freedom in beam bending. Now here, we want to talk about multi-dimensional problem and multi-degree of freedom puzzle. So the most general cases. Okay, so we are going to talk about theory of elasticity in here, chapter 9. But I know that most of you have not heard about theory of elasticity, because usually this is advanced level of course in solid mechanics. So I'm going to explain those basics before we talk about finite element formulation. So if you look at the finite element technique in any commercial, the program, then in solid mechanics, I'm talking about solid and structure, not fluid mechanics or heat transfer. In solid mechanics, there are two types of element. One is called structural element. Okay. And the other one is so-called continuum element. There are two different types of elements to analyze solid and structure. And in simple sense, structural element is like a truss, beam, plate, and shell element. So you know truss and beam. And plate is, beam is going to be one-dimensional, the problem. Plate is going to be two-dimensional geometry. So extension of 1D to 2D in terms of geometry, that's plate. And shell is extension from plate to plate is the flat surface, like a flat. And shell, it means that like any curved surface like this. So mostly, if you look at the actual structural geometry, they have curvature. Your car, if you look at the body of your car, it's not flat. You got some curvature. Ship, aircraft, virtually everything has that, nature of the any kind of the curved shape. So shell is going to be the most general kind of structure element. Okay, so plate, if you use the shell element, then shell represent plate. So usually, if you look at the finite element solution technique, they do not say plate element. They say shell element because this is going to be a set of this problem. So this element can solve this one naturally. So they don't have this one, they have this. Of course, beam and truss, sometimes they don't have truss because truss is going to be part of the beam. So they may have a beam and shell element. Okay, in typical commercial code. Then what is continuum element? Continuum element is like a plane stress and plane strain or solid element, 3D solid. Okay. So what is different between this and that? First of all, let's talk about the basic concept. What is the difference between the concept between the two? So this beam, truss, and shell or plate, this truss element is, in a simple sense, simplified solution. And this is much more rigorous, much more mathematically accurate formulation. So this is simplified formulation, then that's the more accurate formulation. Then why use simplified formulation? Because that's going to be good enough, simple, but produce reasonably accurate solution. So we use that. Then what is the difference between the two? The main difference is going to be equilibrium. So equilibrium means the summation of force equals 0 or summation of moment equals 0. That's equilibrium. Then what is different between a truss structure and continuum, element? Truss element like a beam, then you look at the moment, for example, this moment and that moment. So you look at the overall force and moment, sum of force equals 0, and sum of moment equals 0 in the global sense. We are not looking at, point by point, but overall over the cross section, you got a force and moment, and they equal to each other. Then that's going to be equilibrium. Okay. Then, what is the theory of elasticity? For example, look at one-dimensional problem. I have, load like that one. So total is F. The total is F. And another case, I have load like this. Total is F. And another case, I have load like that, total is equal to F. Right? So they have a different load distribution in the member. Okay? Then structural element, in other words, axial force, bending, thrust or bending and that, they do not distinguish between this and that, because the total is still F, so F equals 0, that's good enough. Okay, but theory of elasticity, we are going to look at the difference, this and that. We are going to have a different stress, different deformation. That's what we are going to follow. Then, when this is critical, if you have a member, and subject to force like this, or subject to force like that, then, for example, in the middle, so-called using Saint-Venant principle, in the middle, stress here and stress here is going to be same regardless. Actual load applied is going to be different as long as the total is going to be same. So this like I use this simple example. If you have a pipe, okay, let's ignore the friction at the wall, and one is going to be pipe like this one, and the other one is going to be pipe like that, but you got the inlet and outlet somehow narrower, okay? And you supply same amount of the flow rate, okay? Then here we expect everything is going to be uniform, then everything is going to be uniform. Again, ignoring the wall, the friction like that, everything is going to be uniform from inlet to outlet, correct? But here, if you imagine that, then it's going to be like that. Right? So sometimes you have some vortex here, vortex in here, like that. So if you look at the profile of the velocity here, different from here. But if you look at the velocity here, that's going to be same as this one. So in mechanics of material or structural element, we are ignoring this aspect. So just looking at the average value. Many times that's good enough. Okay. But if you have a hole, in other words, if I have a plate and I apply load, but if I have a hole, then the stress here is not going to be like this. This is not correct. The actual stress distribution is going to be like this. So-called stress concentration. So this kind of nature, if you use a structural element, then you cannot capture this behavior. So what is the difference? In structural element, as I said, we look at equilibrium in the global sense, all right? But in terms of theory of elasticity, we are looking at equilibrium not only global sense, but every material point. Every small point is going to be in equilibrium. So, in other words, if you satisfy theory of elasticity, then naturally equilibrium is satisfied for structural mechanics. Because look at this way, we have, this country has, let's say 1 million people, of course more than 1 million, but 1 million people. Every single person has a balanced budget. Then whole country is going to be in balanced budget, because everybody's balanced budget, then whole country is in balanced budget. So that's the theory of elasticity. We are looking at the budget balance every individual. Okay, but structural element, they don't look at the budget every individual. They just look at the the balance budget of the whole country. So individual does not satisfy that equilibrium, or does not satisfy the budget. That doesn't matter. That's the different approach. Okay, so again, structural mechanics is going to be approximate, not exact, but again, many times it's good enough and simple enough. That's why we use that, and then we learn that usually in the lower level of the classes. But if you want to solve more complex problem, unfortunately, that is not good enough. You have to really look at the balance of every individual, every material point. That's what we have to do that in theory of elasticity. So that's the major difference. So in other words, when you develop equation of equilibrium, like a beam, if you have a beam, then you cut the beam like that. But in here, we are looking at every element potentially in the beam. So in other words, we are looking at infinitesimal element, dx and dy, and dx, dy mathematically go to 0. So this is going to be approach to single point. So in other words, we want to maintain equilibrium at every single point. That's the main idea. Okay, so that's the the concept of theory of elasticity. Then let's look at two-dimensional problem. So so-called plane stress or plane strain, 2D problem. Then look at the equilibrium. So we are looking at equilibrium at this infinitesimal element, which has length dx dy, and dx dy is going to be approach to 0 eventually. So infinitesimal the length in here. Then let's use some kind of sign convention and then a notation for stress. So sigma, we use the normal stress. Normal stress means what? Stress is going to be perpendicular to the plane, and tau is, we use this information for shear stress. Okay, of course people may use different notation different way, but that's what we are using. So sigma is for the normal stress and tau is for the shear stress. Then either sigma or tau, they have two indices, okay, subscript. So first subscript indicate that the plane, the stress is applied. So how do we define the plane? In 2D, this is X plane. This is also X plane, positive X plane and negative X plane. And this is Y plane. Okay. X plane, Y plane. Then people may say, nominally, I mean, if you look at in terms of 3D perspective, if I have cube like this one, X, Y, and Z, X, Y, Z, then usually this plane we call YG plane, right? And this is called XY plane. And this is called XG plane. That's normally, we call that. But if you do that, then you have to use two components, Y and Z, X and Y, and X and Z. So to simplify that, instead of using XY plane, because this is going to be perpendicular to the x-axis, we call this the X plane. That's the way we are going to use. And this is going to be G plane, and this is going to be Y plane. Okay, so using this, notation X, Y, Z plane. So 2D we have only X and Y plane. So first index or first subscript indicate the stress applied to either X or Y plane. That's first subscript. And second subscript, then the force is either X direction or Y direction. So this one indicates the direction of the stress, and this indicates the plane where the stress is applied to. Okay. So if you look at that, on this plane, this is X plane. So normal stress is going to be sigma. More exactly, this is going to be sigma XX, because first X indicate this is the plane where stress is applied, X plane, and then this is going to be stress applied in the X direction. Okay, sigma XX. Then people prefer to a little bit shorthand notation, so same XX, just use single X, right? But this is more proper, but this is some kind of simplified notation, and many people use this notation too. Okay, then this is sigma also YY more exactly, because this is applied to the Y plane, and then stress is going to be Y axis, Y direction. And this is sigma XX2, because this apply X plane, of course, negative X plane, and then direction is going to be negative X axis. And this is sigma also YY, negative Y plane and negative Y axis. Then what's the sign convention? You got plus, minus X axis, plus, minus Y axis. What is positive stress? Which one we define positive, which one define negative? In this case, very obviously, when stress is going to be tension positive, compression negative. So those are tensile stress, so positive. This is positive. Okay, tension positive, compression negative. That is very clear. Then, in this plane, I have also shear stress, stress tangential. So this applied to X plane. So the first subscript indicate tau, this is the shear, so using notation tau. Subscript is going to be X, this is X plane. And then this is going to be Y direction, so XY. So for positive X plane, when this is going to be positive Y direction, that is defined positive for the shear stress. Okay. Then this one is Y plane, so tau sub Y, and then direction is going to be positive X, so tau sub YX. That is positive. Okay. Then on here, the shear stress is applied to X plane, but this is going to be negative X plane. So when Y is going to be negative, that is going to be positive shear strain on this plane. Likewise, this is going to be tau sub YX. So that's the notation for sigma and tau, XY, YX, etc. in here. So far, so good. All right. Then to complete this so-called free body diagram, so here, let me redraw this picture one more time. I have sigma x is equal to sigma xx. Then here, this is delta x, dx. Then the stress here is not going to be sigma x, right? Because this point and that point, we have separation by dx, right? So what is the component here? Using Taylor series expansion, right? So if you have x plus dx, fx plus f prime x, 1 factorial dx plus higher the term, right? So this is f of x df dx times dx plus higher the term, correct? So here is going to be sigma x plus d sigma x dx plus higher the term. Okay, but as long as dx approach to 0, then this is the linear term, this is the higher the term, so we ignore this one. But you cannot ignore that. That's the critical mistake. If you say dx is small, so I'm going to ignore that one. No, then this is same, so you cannot really represent the value at x plus dx. That means everything is going to be uniform throughout the whole, domain. That is not correct. So you have to include at least, the first order. That's what we have in here. So this is going to be sigma x, then this is going to be sigma x plus partial sigma x dx. So that's from the Taylor series expansion. Likewise, this is going to be sigma y. Then here you got sigma y plus partial sigma y dy. So again, the first order term from the Taylor series expansion. Then this is the shear stress. Then that's the shear stress. And then also this difference is going to be dx. So that partial dx and dx. But what about this shear? This is going to be tau sub yx, then tau sub yx, and this difference is going to be dy. So partial dy. So everything is going to be the first order term from the Taylor series expansion. Make sense? So this is a very general free body diagram in terms of 2D. If this is going to be 3D, then you have to draw free body diagram for kind of a cubic shape, like a dx, dy, and dz. And you got now, one normal stress and two shear stresses in 3D. 1D, one normal and one shear, but 3D, one normal, two shear, every plane, like this, okay? So let's look at 2D. So in here, once you draw this free body diagram, general free body diagram in terms of 2D, then we are going to apply summation of force equals 0, which is always true. Summation of force and summation of moment equals 0. So what is the summation of force? X traction. Okay. Then look at every X component, and if force along X component. So this one, this is the stress times area, because force is going to be stress times area. Area is going to be this, which is going to be dy. And then for simplicity, the z direction is going to be unit value, okay? Because 2D, you can assume whatever value in the z direction, so let's say unit value. Then area of this one is going to be equal to simply the length of the member is going to be dy. So that's the resultant force of this one over this plane. And we assume right side positive. Then this one, sigma x times also dy, but opposite direction compared to that, so minus sign here. What else we have in the x direction? We have this one. So this is more exactly tau sub yx plus tau sub yx dy dy, and then this distance is going to be area of this one is going to be tx, and which is going to be positive extraction, positive, and this one is going to be tau sub yx dx, and opposite direction, negative, and this is the body force. If you have a body force in the extraction, then fx dx dy multiplied by 1, that's the volume, so that's going to be the body force, okay? And what kind of body force we are talking about? Gravitational force or centrifugal force, those are typical body forces you may consider in the system. And the region here, we just use xy instead of yx, then eventually later we can prove that tau sub xy is equal to tau sub xy. Xy, yx, same thing. In other words, tau sub xy, tau sub yx are identical. We can prove that in a minute. So that's why we just used tau sub xy in here. But anyhow, then this is the summation of force in the extraction. What about the y direction? Likewise in here, this component is this one, and multiplied by area, which is going to be dy, and which is going to be positive y direction, the force, and this one, and area dy, negative y direction, so minus, and also this one times area tx, positive direction, and this multiplied by area tx, negative direction, and also if you have a body force in the y direction, then you conclude that, otherwise fx or fy is going to be 0. Okay? Then let's simplify this equation. Let's simplify this equation. So first equation, this times that minus this times that, so they cancel out. Okay? And then this term times that, this time that also they cancel out. So what do you get? Partial sigma x, partial x, dx dy, plus partial tau yx, partial y, also dx dy, if you just swap that, and plus f of x dx dy. So you can divide by dx dy because they are not, 0. So that's going to be sigma x and okay. So that is shown in the next page in here. All right.
What was that? Why is it that the dx/dy disappears?
We just divide by dx dy for every time. And if you do same thing for this, then this term cancel out, this term cancel out, and then divide by dx dy, you come up with this one. Okay. Then we haven't used one equilibrium equation. What is the one? We look at summation of force equals 0 in x and y direction. We have to do summation of moment, right? 2D problem, you have a summation of moment. So let's do summation of moment. Okay, in here, summation of moment, let's say the center, and then assume clockwise positive just in, when you do that. Then the region we pick the center is the region is that now all normal stresses and resultant force do not contribute to any moment about this point because they are going to pass through that point, moment arm is zero. So purposely put that on. Then only shear component produce the moment. So look at this one, tau sub yx plus partial tau sub yx y dy and area dx, and then moment arm is going to be, this is going to be dy over 2, right? And this one, tau sub yx, again area dx, and moment arm is going to be dy over 2, and this one produce clockwise, so positive. And now this one, tau sub xy plus partial tau sub xy dx, and area dy, and moment arm dx over 2, and this is going to be produce moment counterclockwise, so minus, and this one, tau sub xy, and area dy, and moment arm is going to be dx over 2, and again this one produce counterclockwise minus and equal 0. Okay, so what do you see here? This and that is going to be tau sub yx dx dy, right? Dx dy divided by 2, dx divided by 2, so dx dy plus y, and then this one dx and dy square over 2, right? This one. And from here and here, you got tau sub xy dx dy again, minus, let's put minus in here, minus partial tau xy x, and then dx squared dy over 2 equals 0. Right? Professor Good? So we are going to divide by dx dy, dx dy, dx dy, dx, 1 of dy, t1 of dx, and ty, right? Because dx dy is going to be non-zero value. Then what do you see? This is tau sub xyx, and this is tau sub xy. Now, if you look at that, whatever value, multiplied by dy over 2, this one, whatever value, multiplied by dx over 2. So when you again say dx dy approach to 0, in other words, the limit process, this one becomes a single point, then this term and this term disappear, so you have only this term. So that means tau sub xy is tau sub yx. Okay. So those are symmetric index. So x, y, yx, sometimes people do not differentiate. So that's why we did that already in here. That they're a little bit premature without talking about that. Huh? So yx is going to be more appropriate in this derivation. Any question? So if you write the matrix of this one, okay, to represent state of stress matrix, sigma, then you can put the sigma x, tau sub xy, and tau sub xy and sigma y. So represent stress in this manner, in two-dimensional case. So this is going to be symmetric matrix, okay? So sigma x, sigma y, tau sub xy are 3 stress components in 2D. And this is equation of equilibrium. Many times Fx, Fy are zero. We know that body forces, but otherwise you can include that. Then if you look at that, now I'm going to generalize this one for 3D. Right? This is 2D. Yes. Oops. What's going on? Let me. Okay. Michael, can you see the screen?
Yes, I can.
Thank you. There was a little technical problems, but now should be okay. So this is the 2D equation of equilibrium. If you're going to expand this one to 3D, equation of equilibrium is going to be partial sigma x dx plus partial tau xy dy plus partial tau xz dz plus f of x equals 0 and partial tau xy dx plus partial sigma y dy plus partial tau yz dz plus fy equals 0. And the last one, partial tau sub xz plus partial tau sub yz plus partial sigma z plus fz equals 0. So you got 3-dimensional equation of equilibrium for that one. Okay. So this is 2 equation and 3 equation. And again, this is summation of force in x, y, and z direction. The moment equation give you tau sub xy, tau sub yx, and tau sub yz is tau sub gy, and tau sub xz is going to be tau sub gx. So they produce 3 relationship from moment equation. So in terms of 3D, the stress state is going to be expressed this way: sigma x, tau sub xy, tau sub xz, and tau sub xy, sigma y, tau sub yz, and tau sub xz, tau sub yz, and sigma z. Okay, that's for 3D. Instead of stress, so we have a 3 component, 1, 2, 3, 3 component, right? And here 1, 2, 3, 4, 5, 6. So 6 component because those are symmetric. So 6 stress and 3 stress depends on 2D or 3D. And equation is 2 equation for 2D, 3 equation for 3D. What does it mean? If you look at the number of equation, equilibrium equation, and number of unknown, what do you see? Let's start with the 2D. How many unknown quantities? Body forces are given. So don't include body force. Fx, Fy are either 0 or non-zero, whatever this is given. So what are unknown component in this 2D equation of equilibrium?
Would it be three?
3, sigma x, sigma y, tau sub xy. 3 unknown, right? And how many equation? 2 equation. So that means naturally, statically indeterminate. So zero elasticity is statically indeterminate problem. There's no statically determinate problem in terms of zero elasticity. Okay, you cannot calculate, you cannot find stress from equation of equilibrium only. That's why structural element, so for example, beam and truss or those kind of nature, you can have statically determinate problem, right? You can find the force, and from there you can find the stress. So much simplified, because in real nature, the problem is going to be statically indeterminate. And if you look at 3D, even that is worse. Now this has a 2 equations, 3 unknown, a little bit close, just one different. But if you go to 3D, how many equations? 1, 2, 3, right? How many 3 equations? How many unknown? How many unknown? I'm showing that. 6 unknown, right? 6 component because of symmetry. So 6 unknown, 3 equation, then definitely short of the equation, right? And also now one clear difference between this and structural element formulation like a beam or truss. Now your equilibrium equation is differential equation, especially partial differential equation. In beam and those elements, when you drive, in undergraduate class, mechanics material class or structural mechanics class, your equilibrium is going to be just algebraic equation. Summation of force equals 0, summation of moment equals 0, right? But now in zero elasticity, your equation of equilibrium is going to be partial differential equation. That is much more difficult to solve. That's why people prefer mechanics material as structural element concept as long as it provides the right solution for you. Okay, but some example we talk about today, unfortunately, they cannot capture the solution. Then you have to solve the problem using theory of elasticity, so-called continuum element in here. So anyhow, so that's the first set of equation of equilibrium. Okay, and now this is statically indeterminate problem. So you have to introduce so-called geometric comparability. That means in here, we have to introduce additional equation. One of them is going to be constitutive equation. What is the constitutive equation? Constitutive equation is going to be the relationship among stress and strain. Okay, so in other words, if you remember in your undergraduate program or some earlier classes, if you do some tensile test of, for example, dog bone shape, tensile test, and then if you plus stress and strain, one-dimensional stress strain, then it's going to be like this. And depending on the nature of the material, something like that, right? So we are talking about this linear elastic region, this one. So this is so-called elastic modulus, right? So sigma is E epsilon in one-dimensional case. This is called the Hooke's law, right? This is the Hooke's law. And then if you extend this one to 2D or 3D, let's say if I have a cube, let's do 2D, easier to visualize. So if I apply sigma x, this is x and y plane, right? If I apply sigma x, then strain in x direction, assuming this is isotropic material. Isotropic means property same in every direction. So epsilon x is going to be sigma x divided by elastic modulus, right? From Hooke's law. So epsilon is sigma over E, correct? Then what about the strain in the y direction? As you apply the stress in the x direction, what is strain in the y direction? No strain? Or positive, negative? What do you see?
Should be negative.
Negative, but how much?
Depends on the material, but a
So-
fraction of the X strength.
Depending on material, and then that material property we call so-called Poisson's ratio, right? How much it changed transversely as you apply that the loading longitudinal, that's the Poisson's ratio. So that's going to be negative nu sigma x over E. Okay, that's the Poisson's ratio. And Poisson's ratio we define, very interesting, you know, when you apply that, epsilon x is positive, but epsilon y, this is going to be, I mean, if you can visualize that it's going to be deformed like that, right? So epsilon x is positive, but epsilon y is negative, right? So Poisson's ratio is that epsilon y over epsilon x, then it becomes negative. So people didn't like negative, so they define absolute value positive. Okay, so that's why we have a minus sign in here. Okay, then linear elastic system, you can apply principle of superposition. In other words, you can apply one by one. So sigma x, then that. Now on top of that, now if you apply sigma y, then let's look at this one. What is going to be strain in the y direction due to sigma y? If this is going to be isotropic material, property same, both x and y direction, then that's going to be sigma y over E, right? Then here we have Poisson's ratio, so negative nu sigma y over E, right? So far so good. Then if you look at this one in 3D perspective, then that's going to be nu sigma x over E, nu sigma y over E, okay, because of sigma x and y. And then if you apply sigma z also in tension direction, then that's going to be sigma z over E, and that's going to be nu sigma z over E, and that's nu sigma z over E, right? So if you rewrite this one, matrix form, epsilon x, epsilon y, and epsilon z, okay, then that's going to be 1 over E, 1, negative nu, and sigma x, sigma y, and sigma z. Okay, and nu 1, negative nu, 1. Okay. Have you seen this kind of expression before? If this is going to be 2D, then of course we are looking at only this 2 by 2 component, right? Those are ignore. and 3D like that. Then what about the shear? Shear. So if you apply shear like this, then it's going to deform like that. Okay. And shear does not induce any length change, but the shape change. And that material property we call shear modulus. So that's going to be tau xy over g. And same thing, gamma yz is going to be tau yz over g. And gamma xg is going to be tau xg over g, isotropic material and shear modulus, right? Those are shear modulus. So eventually you can write, if you include the tau sub xy and tau sub yx and tau sub xg, so 6 by 6, then that's going to be extended to from 3 by 3 to 6 by 6, okay? But those are going to be diagonal matrix. So once you have that, then standard notation is that we want to write sigma x, sigma y, sigma z, etc. in terms of epsilon x, epsilon y, and epsilon z, etc. like that. So we have to invert this matrix, okay? So this invert matrix, we call matrix D, okay? If you invert, that's going to be matrix D. So D depends on the material, 1D, 2D, 3D, or this is going to be isotropic, orthotropic, and isotropic. We'll talk about that in a minute. But depending on that, this is going to be that. But in general, we have relationship between stress strain in this manner, and then D is going to be the constitutive matrix relating stress and strain. Okay, so in isotropic material, inverse of that is going to be equal to D, and especially plane stress, only looking at this one, right? Then that's going to be equal to, inverting that is going to be equal to theta. Okay, that's the shear modulus. So in other words, the shear modulus for isotropic material has relationship like this. Okay, for isotropic material. So in other words, shear modulus is not independent. If you know elastic modulus and positive ratio, then you can calculate shear modulus from here. It's not an independent problem for isotropic material. So far, so good. Now, let me talk about one more thing, and then I'm going to just stop the discussion. What I said was that, people define purposely that positive ratio is going to be this way, absolute value. So epsilon y minus epsilon x, and absolute value, that's the positive ratio. Okay? And most material is going to be like that. But recently, not very recently, but people propose some kind of material design, for example, like this. Okay? So it's like a bow tie, right? If you pull this one, what do you see? What do you expect? If you pull this way, then this is going to expand. Correct? Right? Because the nature, this is going to expand. Then, in terms of positive ratio, they call this going to be negative, because we define using that absolute sign, right? So we define positive ratio as that this way, right? Because mostly people look at this problem. But now when situation like that, and then it cannot be same as that. So to really differentiate this one, they say this is going to be negative positive ratio. Even they're expanding. Okay, based on our rotation. And this is called auxiliary, design. They call auxiliary material, but it's not really material. That's going to be a design of geometry. So this is going to be auxiliary structure. Right? Then they say negative persuasion. Okay, let me stop here. And then next Tuesday, we don't have a class, so class is gonna continue next Thursday. Okay? Any question up to this point?